And I'll give you a visual tomorrow on this. Actually, I'll give you a lot of visuals. In the equation ax equals lambda x, all right, that's the case where you have equality. We're defining the scalar as the eigenvalue of a, right? Because what's happening is you're having two vectors that are not changing in size, right? So you're maintaining the vector x. The only difference would be that a and lambda might be two different things, all right? So it's possible that a is half as much as lambda, or twice as much, or whatever. We'll get into how that works in a few minutes. Vector x equals 0 is called an eigenvector of a associated with eigenvalue lambda in the null space of a minus lambda I sub n is called the eigenspace of a associated with eigenvalue of lambda. We'll talk about this in a little bit, but a minus lambda I is also known as the characteristic matrix. So, and we'll have a characteristic equation in just more vocabulary terms. All right. So, the derivation, because the derivation is going to give us an actual process. I just didn't feel like writing it out, so one of the things I did last night was just to type it up. Did I start the recording? Good. So you have ax equals lambda x. Subtract the lambda x from both sides, factor out the x, and you have this expression a minus lambda. The issue is, though, and it's a pretty significant issue, a is a matrix, lambda is a scalar. You can't just subtract a number from a matrix. You can't just do like matrix 2, 0, 0, 2 minus 4. But it doesn't work that way. In order to do subtraction, you have to have consistent dimensions. So what we do is we manufacture consistent dimensions by multiplying by an appropriate identity matrix, right? So the identity matrix I would have the same dimensions as whatever the matrix A is, all right? So, and in doing so, if I wanted to, I could factor out a -1, which would allow me to reverse the order. So you can go with either version of this. The one that I prefer is actually the first one. I just find it gives a cleaner algebra, which means something that you'll see in a minute. So anyway, we're looking for a non-trivial solution when we solve this equation, because you can say, I mean, you can easily solve this equation by saying, yeah, both, x is the 0 vector, left equals right, because 0 equals 0. So, I mean, it's one of those things like, I want to prove a trig identity. Tangent equals sine over cosine. All right, well, how do I prove that they're equivalent to one another? Multiply both sides by 0. 0 equals 0, done. Well, you're not really telling me anything. In that case, it's completely invalid, but in this case, it's a solution. It's just not an overly meaningful one. All right? So we're looking for free variables. We're looking for non-trivial solutions. If we're looking for free variables, then we're looking for cases in which the determinant is equal to 0. Right? So we want to have, and that's because there's going to be rows containing all zeros. If you have a free variable, there's going to be a row somewhere along the lines that has all zeros in it. So what we're going to do is use what's known as a characteristic equation. That doesn't need to be here anymore. Characteristic equation of A to help us determine the eigenvalues. Once we have the eigenvalues, then we'll use those to determine what are known as the eigenvectors. Right? Those, again, are the vectors that are either scalars or exactly identical in such a way that it does not change the matrix. All right, so solve that example if you want. But let me take you through something a little bit more hands-on. All right, so we'll start off with just whether or not it's an eigenvalue. There's a couple of ways to handle it, but The one way involves using the characteristic equation, which is the way I'm going to do it. All right. So we know that the determinant, well, we just learned. Now again, you have a choice, and I'll leave it up to you. You have a choice. You can use either this variation or this variation. They're both going to amount to the same thing. But like I said, I like the a minus lambda I, or I lambda. It's just a personal preference. But you can go the other way around. It's not going to make a difference. To get an eigenvalue, I need that equation to be true. All right. So I have my A. I need lambda I. Well, so I need lambda multiplied by a square matrix with the same dimensions as A. Has to be an identity matrix, so 1, 0, 0, 1. So lambda I, or I lambda, doesn't matter, would be lambda 0, 0, lambda. I'll use actually just a bracket because I'm about to just do the operations anyway. All right, so and the reason I like this variation more is, especially for the larger matrices, it preserves positive signs. It just feels nicer. So anyway, each entry in A, I'm going to subtract from that each corresponding entry in I lambda. So -1 minus lambda. Well, we're not assuming that yet. 4 minus 0, 4, 6 minus 0, 6, and then 9 minus lambda. All right, so the determinant of this has to be equal to 0. So at this point, if you wanted to, you could plug in the -3 and test it out, but I really haven't shown you how to actually find eigenvalues yet. So this might be a pretty good opportunity to do that. So diagonal down. Minus diagonal up. 24. I don't know why I saw a 9 there. Distribute. What do we got there? -8 lambda. I think so. So lambda squared minus 8 lambda is it minus 33? All right, so lambda minus 11 lambda plus 3 equals 0. So I have two eigenvalues, lambda equals 11 and -3. All right. So the other option would have been, if there's sort of a question on the test, you can necessarily figure all this out. Plug in your -3, get numerical values, do diagonal down, diagonal up. So this is actually how you find eigenvalues, which I think is infinitely more important. That being said, if you're dealing with a 3x3 matrix, shortcuts can be a little bit more beneficial. So again, it's all coming back to the characteristic equation. So we're subtracting from it an identity matrix that's multiplied by the scalar lambda, which basically means that everything else, if you do it in this fashion, And again, the reason why I like this is that it preserves the sign. It's going to keep everything except for items along the main diagonal the same, right? Because all you're doing is subtracting zeros from those. So along the main diagonal, you're subtracting a lambda. Everything else is going to stay put. So it kind of streamlines the process a little bit. A minus I lambda would be 4 minus lambda, negative 2, 3, 0, negative 1 minus lambda, 3, negative 1, 2, negative 2 minus lambda. All right. Now, if you wanted to, because like I said, in this case, good opportunity to learn actually how to find an eigenvalue. Here we'd have to do cofactor expansion in order to do it, and we'll cross that bridge when we get to it, but there's no reason to do it now. So let's do it through direct substitution. If lambda is equal to 1, then we would get 3, negative 2, 3, 0, negative 2, 3, negative 1, 2, negative 3. All right. Now, if lambda is equal to 1, then I lambda is really just I. So really just subtracting the identity matrix. So you could do a quick double check on that. We subtracted 1 down the main diagonal. But basically what I need here is the determinant of A minus I lambda, where lambda is equal to 1. I need it to be equal to 0. You do it cofactorly if you want, or you can do it calculatorly. Slow calculatorly. Would like to have that like nice obvious relationship, like a nice row of all zeros or something, but dang. Hopefully I typed it in correctly. Determinant, matrix A. Oh, you son of a gun. I swear I just typed it in. I put it in J? All right. That's new. Right, 0. So it is an eigenvalue. Now we need to find the corresponding eigenvector. All right, so to find an eigenvector, you have to solve the example here if you want to look at that. There's also a procedure, but basically you're solving a homogeneous equation using that eigenvalue. So you create the new matrix based off of your characteristic matrix, right? So your eigenvalue, in this case we had a 2 and a 3. So if I plug in a 2, you get negative 1, negative 1, 2, negative 2, right? We solve that equation, that homogeneous equation, and what that'll give us is the eigenvector that's associated with the eigenvalue. All right. It's just the signs are different in this case because when I typed this up, I hadn't fallen in love with A minus I lambda yet. So what can you do? What can you do? All right. So lambda is 1, so we have again this guy here. solve the homogeneous equation. So take your matrix J for some reason and row reduce that. Wait half an hour for a button to actually work. All right, so let me just snip it. So we got this bad boy here. All right, so we're solving the equation A minus I lambda x equals 0. All right, so we're solving for x. So here we're getting x1 equals 0. x2 equals 1.5 x3, and x3 equals x3. All right, so that's our free variable. All right, so what that's telling me is that x, my eigenvector x, is going to be some scalar multiple of 0, 1.5, 1. All right. I'm like dreading going back to this calculator because it's ever since I put the program in, it's been running so slow. Oh, this is already manipulated. All right, so let me put in my original matrix. Which will take like the rest of my life to do. What's that? Piece of garbage. All right, so I have matrix A, matrix B. I'm going to do a quick multiplication, relatively quick. This calculator is looking at a different universe. All right, so I took my original matrix, multiplied it by my eigenvector, and got the same exact vector. Now, one thing that you can do is apply a scalar to that eigenvector and see what impact it has. So just double each entry. Triple, quadruple, whatever you want. Negate. It's all double. So 0, 3, 2. Eventually. right? So basically, it's a process, and it feels an awful lot like a steady state vector. The idea that you're creating a multiplication process that allows you to maintain the value of the same, of whatever the vector is that you're starting with. Right, but the eigenvector is the basis of whatever that, I mean, they call it an eigenspace, but this is the basis of that transformation that allows you to maintain the same span, right? So if you're looking for, if you have like 5 different eigenvalues, then you'd be spanning using 5 different vectors. That would be your eigenspace. Right? So everything could be written in that eigenspace as a linear combination of those eigenvectors, or like obviously the scalar multiples of those. All right. So the same idea for number 3. The basis of the eigenspace is basically finding all the eigenvectors that go along with the eigenvalues. All right. So. Meh. 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 Here the last 2 are fun ones. Little a plus bi action, like imaginary is what. And I won't ask you to do this. So that's where we'll pick up to. All right. Well.